So we will see radical expressions where we have those radical terms in there, but there's also other stuff going on. And so in those, we often are going to want to simplify first and then mess around with it. Let's look at some. Now in this one, you just might notice off the bat that there's nothing to simplify under the radical. So the square root of 3 and square root of 3, like that can't get any simpler. When you see these, I want you to think about, I have 5 root 3s and I have 4 root 3s. How many root 3s do I have? You can almost think about this like it's a unit. I have 5 of them and 4 of them, so altogether I have 9 of them. I can do that because they're both square root of 3s. I can't add apples and oranges, but here I have apples and apples. Now on this one, I have 7 root 3 and I have 5 root 12. I can't just say, okay, 7 plus 5 is 12 and be done, because I'm not using the same kind of units, as it were. So we're going to first try to simplify this root 12. So 7 root 3 is just hanging out. And now remembering how to simplify that term, 12 is going to get broken up into 2 times 2 times 3 if I use its prime factorization. And the square root of 2 times 2 is just 2. So I can bring that to the outside. Now I have 5 times 2, and what's left is still a root 3. Now this is looking like something I can simplify. 5 times 2 is 10, so I have 7 root 3s plus 10 root 3s, and I have 17 root 3. When you sit down to these, you should first remind yourself, okay, there's probably a similar thing in here, otherwise they wouldn't have given me this problem. So the first thing you want to do is not panic. The second thing you want to do is try to simplify these radical terms. So square root of 8, I know that that is 4 times 2 is the same as 8. How about 18? What is that guy? I could write that as 9 times 2. 9 is a perfect square. Remember, if you have those perfect squares kind of in your head, it's going to be helpful. And then 50 I can write as 25 times 2. And now this is looking really nice for me because I've got perfect squares, and then the leftover in each of those radicals is just 2. So I think that's going to be great. So I have 3 times the square root of 4 is 2, and I still have root 2 underneath. 4 times the square root of 9 is 3, and 5 square root of 2. So 6 root 2 plus 12 root 2 minus 5 root 2 is going to be 18 minus 5. We've got 13 root 2 at the end. Now you're going to often come across these sort of formats when you're doing the quadratic formula, right? Where you've got something plus or minus the square root of something over something. So I just want to practice really quick how we can simplify these when we come across them. This one, I hope you recognize right off the bat that the square root of 121 is a nice number. 121 is one of those perfect squares. So this becomes 4 plus 11. Now we can add those together, and we can simplify that to 5. Here, square root of 24 is not a perfect number, so let's break that up first. So I have 4 plus, and then 24, when I break that up, let's see, it's 4 times 6, and I could break 6 into 2 times 3, but neither of those are perfect squares, and 4 is already a perfect square, so I'm okay with that so far. So I have 4 plus square root of 4 is 2, root 6 over 10. And now, if there's a number that goes into each of my terms, I can divide it out. So I notice that 4 and 2 root 6 and 10 all have a times 2 inside them. So I can divide out 2 from each of them. 4 divided by 2 is 2. 2 root 6 divided by 2 just leaves me a root 6. And 10 divided by 2 leaves me 5. There's nothing more I can do to simplify this. It's all done. Notice I divided 2 out of this entire term. I didn't take it out of both the 2 and the 6 because, first of all, I can't take a 2 out from under that root sign. But second of all, when I'm dividing 2 root 6 by 2, I only want to take out 1 2.